Welcome to online video training for the CTI Workbench Integrated Development Environment. This is Course 1, Part 4, Programming in Ladder Diagram. Running time, 18 minutes. Let's get started. Ladder diagrams are specialized schematics, commonly used to document industrial control systems. They're called ladder diagrams because they resemble a ladder, with two vertical rails, and as many rungs, as there are control circuits to represent. In Workbench, ladder diagrams consist of these components: rungs, contacts, coils, power rails, function blocks, labels and jumps, comments, and, optionally, structured text expressions. Let's see how these components are used to build a ladder diagram. A ladder diagram is a sequential list of rungs. Each rung represents left-to-right Boolean power flow, that begins with a power rail, and finishes with a coil or a jump symbol. Each rung is identified by a default numbered label, displayed on the left of the power rail. The rung label can be used as a target for jump instructions. You can edit the rung label by double-clicking in the rung head, on the left margin. The ladder editor enables you to manipulate whole rungs, by selecting only their head, in the left margin. Once selected, you can use normal, cut, copy, and paste operations. The contact is a basic graphical element of the ladder language. A contact is associated with the Boolean variable attached to its graphic symbol. This variable is often, but not always, tied to a physical input point. If the contact is true, then power passes through it to the next part of the rung. There are 4 contact types in Workbench. You can change the contact type by highlighting it and pressing the space bar. In a normal contact, power flow occurs when the variable is true. In a negated contact, power flow occurs when the variable is false. In a positive pulse contact, power flow occurs on the rising edge, when the variable transitions from false to true. In a negative pulse contact, power flow occurs on the falling edge, when the variable transitions from true to false. You can insert and arrange contacts in any desired order, and parallel branches can be included. The coil is another basic graphical element of the ladder language. A coil is associated with the Boolean variable attached to its graphic symbol. The coil sets the value of its variable according to the rung state on its left side. There are 6 coil types in Workbench. You can change the coil type by highlighting it and pressing the space bar. The normal coil sets its variable value to the same as the rung state on the left. The negated coil sets its variable value to the negation of the rung state on the left. The set coil sets its variable to true if the rung state on the left is true. Otherwise, there is no change. The reset coil sets its variable to false if the rung state on the left is true. Otherwise, there is no change. The positive pulse coil sets its variable to true for one scan, when the rung on the left goes from false to true. The negative pulse coil sets its variable to true for one scan, when the rung on the left goes from true to false. Vertical power rails are used in ladder diagram for representing the limits of a rung. The power rail on the left represents the true value and initiates the rung state. The power rail on the right receives connections from the coils, but has no influence on the execution of the program. When programming, you can use the Align Coils icon to line up the right power rail of all your rungs. Function blocks allow you to perform complex and non-Boolean operations in your ladder diagram. To insert a function block, just select it in the object pane, drag it into the ladder diagram, and connect its inputs and outputs. The name of the instance must be specified on the function block. Here, we have added a timer. Labels and jumps allow you to control program flow, conditionally skipping parts of your ladder diagram during operation. The jump instruction jumps to another rung in the program by label. To insert a jump instruction, make sure your destination has a label. Then go to the desired insertion point in your ladder, and click the Insert Jump icon. If you want the jump to be conditional, enter the desired contacts in front of the jump. Then double-click the jump instruction, and select the label you want to jump to. To help with program documentation, the ladder editor allows you to insert comment text at any point in the ladder diagram. The comment can be a single line of text, and is inserted between two rungs. The comment text is displayed on a double line in the diagram. Comment text has no meaning for the execution of the ladder program. To change the text of the comment, simply double-click on the comment line. Complex expressions can be entered on any graphic element and ladder diagram. This feature allows you to simplify your ladder when simple calculations are needed. For example, suppose that in our previous illustration using the jump instruction, we wanted to execute the jump only if a tank level was greater than 100. To accomplish this condition, we'll just create a variable tank level and make it an integer. Then, on the contact which conditions the jump instruction, we just enter tank level greater than 100. The vertical toolbar on the left side of the editor contains buttons for inserting items in the diagrams. Items are inserted at the current position in the diagram. Insert contacts before, after, and in parallel. Insert a horizontal line. Insert function blocks before, after, and in parallel. Insert jump. Insert coil. Insert new rung. Insert comment. And align coils. All available operators, functions and function blocks, are listed in the object selection pane at the lower right of the screen, grouped by category within folders. The category, All, enables you to see the complete list of available blocks. The category, Used, shows all blocks which are used in the currently open editing window. The category, Project, lists all UDFBs and subprograms in the current project. To insert a block, simply select it in the list, and drag it with the mouse to the desired position in the program. Press the F1 key when a block is selected, to get help about its function, inputs, and outputs. Once the block is inserted in your program, you can also double-click the mouse on the block to change its type, and set the number of input pins, if the block can be extended. For a valid ladder program, variables must be attached to all contacts, coils, jump instructions, and function blocks. In addition, all inputs and outputs of functions and function blocks must have variables or constants attached. Since we haven't observed these rules, our sample program will not compile. To find the errors reported by the compiler, note that the error locations are included in the output. In our program, the first error is located at 1,5. By moving the cursor around and noting the location displayed in the status bar, we can find the cell which generated the error. If you need to zoom in, to see parts of your program more clearly, you can use the zoom selections in the View menu. You can also drag the separation lines in the vertical and horizontal rulers. For editing your program, cut, copy, and paste is supported. You can copy entire sections of the program, or just part of a rung. That completes all the skills needed for programming in ladder diagram. Now, let's do some exercises. In exercise 1A, we'll write a program in ladder diagram to control a conveyor. The conveyor system has the following control actuators and sensors. Conveyor 1 stop is a momentary switch, normally open, which stops conveyor 1 when closed. Conveyor 1 start is a momentary switch, normally open, which starts conveyor 1 when closed. Conveyor 1 overload is a normally closed contact, which opens when an overload is detected on conveyor 1. Conveyor 1 run, closed, true, to run conveyor 1, open, false, to stop. Conveyor 1 safety stop is a normally closed contact, which opens to stop conveyor 1. Make one rung of ladder which controls conveyor 1, according to the following rules. Pressing the momentary start switch starts the conveyor. The conveyor remains running when the switch is released. Pressing the momentary stop switch stops the conveyor. If the overload contact opens, the conveyor stops. If the safety stop opens, the conveyor stops. We'll start by adding a new program. Call it Exercise 1A. Programming ladder. Then open it for editing. Next, we'll create all the needed variables. Conveyor 1 stop. Conveyor 1 start. Conveyor 1 overload. Conveyor 1 run. Conveyor 1 safety stop. All are booleans. The program can be done in one rung, with 4 contacts, and then a parallel contact for latching in the run coil. We use a negated contact for the stop switch, and then normal contacts for all the others. Finally, we need to set an initial condition of true for the overload and safety stop variables, since they are normally closed. This would not be necessary in a real system, because the I/O scan would set these values for us when the program starts. We'll tidy up by moving the program we just created into the Programs folder. Then we need to edit the cycle settings to disable our practice program, since it has errors in it. Compile our project. No errors. And now, run in the simulator. To test our application, turn the conveyor on, and make sure it stays latched on. Activate the stop button, and the conveyor goes off. Turn it on again. And activate the safety stop. Conveyor goes off. Turn it on again. And activate the overload. Conveyor goes off. Everything is working. A successful first application. In Exercise 1B, we'll add a second conveyor that has an identical set of sensors and actuators. Then add logic to control Conveyor 2, according to the following rules. Conveyor 1 must be running to operate Conveyor 2. Anytime Conveyor 1 stops, Conveyor 2 should also stop. Pressing the momentary start switch starts the conveyor, and it remains running when the switch is released. Pressing the momentary stop switch stops the conveyor. If the overload contact opens, the conveyor stops. If the safety stop opens, the conveyor stops. Add the variables for Conveyor 2. Conveyor 2 stop. Conveyor 2 start. Conveyor 2 overload. Conveyor 2 run. Conveyor 2 safety stop. Then add the rung for Conveyor 2. To save time, we can copy the rung from Conveyor 1. Insert a contact at the beginning, to require that Conveyor 1 must be running, to operate Conveyor 2. And relabel all the contacts and coils for Conveyor 2. Set the initial values for the overload and safety stop. Compile. And run in the simulator. Turn on Conveyor 2 start. The conveyor doesn't start because Conveyor 1 isn't running. So start Conveyor 1. And now start Conveyor 2. It comes on. Check the stop and safety stop switches. And finally, verify that if we turn off Conveyor 1, Conveyor 2 also goes off. And it does. Another successful application. In Exercise 1C, 2 safety warning horns are added, one for each conveyor. We'll add logic to our program to sound a warning horn for 5 seconds after pressing the start button, before the conveyor starts. We'll use the pulse timer to sound the horn on the push button, then use the falling edge of the horn signal to start the conveyor. We'll create the variables we need. Conveyor 1 and Conveyor 2 horns. Timers for the 2 horns, with type TP, pulse timer. and two variables to hold the elapsed time for the timers. These need to have the data type, time. To operate the horn timers, we'll add two rungs to our ladder diagram, one for each timer. Then, insert a pulse timer in each rung. The conveyor 2 rung will have an extra contact, so we can make sure conveyor 1 is running before starting conveyor 2. Put the conveyor 1 start switch on the first rung. Set the timer for 5 seconds. And attach the horn 1 contact. Then attach variables to rung 2, and attach the elapsed time variables. We need to modify the conveyor control rungs, so that the falling edge of the horn timer replaces the previous start switch. We forgot to assign the timer variables, so we'll do that now. Let's add a couple of comments to describe what's happening. Then compile. No errors, so go to simulation. To test our completed program, we'll turn on the conveyor 1 start switch. If everything is working, we should see horn 1 come on for 5 seconds, then horn 1 goes off, and conveyor 1 comes on. That's exactly what happens. Conveyor 2 should operate the same way. And it does. Another successful application. In the Workbench Course 1 training manual, there are 3 more exercises to help you develop proficiency with programming in ladder diagram. Exercise 1D implements a simple volume control. Exercise 1E simulates a car park control. And in Exercise 1F, you will develop a basic heating control. We encourage you to complete those exercises before proceeding to the next section of Training Course 1. That completes Course 1, Part 4. Here's a summary of what we've covered so far. Introduction to Workbench in IEC 61131. Basic concepts of Workbench. Getting started programming in Workbench. And programming in ladder diagram.